Alright, so we introduce the idea of center of mass. That the center of mass is sort of difficult to explain. It's as if you have a system of objects, and if you were to represent that system of objects by one point, that point would be the center of mass. It is another way to refer to it is that it is the weighted average of all of the masses making up the system. That this mass being greater than that mass should get more weight, and so the center of mass moves closer to this than it is from that one there. Here you have a hammer being thrown through the air, a very complex motion, but if we were to represent the hammer by one point, that point would be the center of mass, and this red arc here is the path of the center of mass, and you can see the center of mass is located way up towards the top of the hammer, that the head of the hammer gets a lot of weight, its mass, and this mass down here being less gets less weight, and so the center of mass is skewed way towards the head. The path followed by the center of mass is a very simple parabolic trajectory, whereas if you were to try to look at the whole system, the whole hammer, very complex motion going on there. So there is advantage to this center of mass idea. So here again, here's the idea of a weighted average, that I will take each little bit of mass, I will take its location, and I will weight that location by how much mass is at that location. And then we'll go to the next bit of mass, I'll take its location and give that location a weight according to how much mass is located there. Excuse me, I will add all of those up and then divide by the total mass, and this is what we call a weighted average. And that value that you get out of this is the center of mass, the location of the center of mass. We can write it symbolically this way. I don't know if that looks better or not. This is perhaps easier to look at. That's the total mass, and here's each of the individual masses and the location of each of the individual masses, and each of those locations is weighted by how much mass is there. Add them all up, divide by the total mass. The center of mass is very analogous but not identical to center of gravity. That this would be, here you're taking all the locations of all the masses and weighting them by how much mass is there. Here you would take the location of all of the weights, if you are. Look at how much gravity pulls on each point. Look at the weight at each point, and weight each point by how hard gravity is pulling on it. And that gets you center of gravity, which is a term we use a lot. Very, very close to the same, but not identical. And the question is, how could they not be identical? How could the gravity not correspond exactly to the mass? After all, gravity is mass times the field strength, mg, and then it comes to you that the pull of gravity does not stay constant. And so if you have something like the moon relative to the earth, and this is actually to scale, the moon is about a third to a quarter its diameter compared to the earth, and it is 60 earth radii away, which is pretty far out there. Actually, it's relatively close in astronomical terms, but the gravitational pull on this side of the moon is going to be greater than the gravitational pull on the far side, because gravitational force varies inversely with the square. And so in terms of center of gravity, this side would get greater weight, weighing in the weighted average, than that side, whereas the center of mass might be located at the geographic center of the moon, assuming that it's uniformly distributed mass. The center of gravity would be slightly closer to the Earth because of the greater weight, the greater gravitational field strength on the near side of the moon. That's trivia, but I thought it might intrigue you. Okay, so here's an example. We have these three masses, this discrete distribution of three masses. Here are the masses, and here are their locations, and I want to find the center of gravity of those three. And we could start by just sort of saying, well, I've got 6 kilograms down at this level and 6 kilograms up here, so the center of gravity ought to be sort of halfway in between those two. And I've got 8 here and 4 there, so the center of gravity ought to be 2/3 of the way back here, that it ought to be someplace sort of like that, with this 8 getting twice the weight that the 4 does, pulling it back this way, and center of mass, someplace like that. But the actual finding of that would be a matter of taking this location x and weighting it with a weight of 2, and taking this location for x, which is a 1, and weighting it with a weight of 6, and this location for x of 4, and weighting it with a weight of 4, adding up those weighted values and dividing by the total mass to get the center of mass, the x center of mass. And similarly for the y center of mass, I would take this, which is at location 1, and I'd weight it 2. This is at location 2, and I would weight it 6. And this is at location 1, and I would weight it 4, and then divide by the total mass again to get a 1.5. So indeed, y-wise, it's halfway up from 1 to 2, and x-wise, it is 1 unit away from this, and 3 units away from that. Is that right? It's at 2, which is 1 over here, and then to get to 4, I would have to go 2 more. Yes, 1/3 of the way over, because of that weighted average. But consider that you could have made your life a little bit simpler by, instead of accepting this coordinate system that they gave you, creating a new coordinate system that put the origin right here. And in that case, this one would be at 0, 0. It would get no weight. Would have no value when you multiply 2 times those zeros. And this would also be at 0, so it would get no weight. And you would have this one, which would be at 3, right? Because I made 1, 1 be my origin. This would be at 3, and it would get a weight of 4, and I divide by 12, and I get a 1. Different value that I got here, but that's because it is 1 in this new coordinate system, which has a 0, 0 right here. And similarly in the y, this would be made null by being the origin. This would be 1 up, it would get a weight of 6, and this would be at 0, getting a weight of 4, and so perhaps the arithmetic would be a little bit easier there, that your center of mass would be 1, as we indicated, or if you have the origin at a true 0, 0, then at 2, and this one comes up with a 1/2, or if you put the origin at 0, 0, a 1.5. So there's a little gimmick that you can use to possibly make your life a little bit easier, and you can make it significantly easier by your choice of where you put the origin. Now we have not a discrete distribution where I would take a discrete summation of those weighted locations, but a continuous distribution. And how do you find the center of mass of this object? And let us assume it is uniform. It gets even more interesting if the density changes, and so the mass of an equal area here is not the same as the mass over here. But what I'm going to do is to take this and cut it up into little chunks. I'm going to take this continuous distribution, cut it up into little chunks, and I will take each of those little chunks and I will take its location and weight it by how much mass is at those little chunks. And then what I'm going to do is to let the number of chunks increase so that the size of the chunks goes infinitesimally small, and then we will end up with a continuous summation. Each location being weighted by the mass that's there, that little infinitesimal of mass. And I will add them all up continuously and then divide by the total mass. And so there is a formula for the center of mass where you have a continuous distribution. And I hope you can see right away that, okay, that's very glib to say, but how exactly would you evaluate such an integral? Through what limits would you go to get a value here? And Yorick, there's the rub, and we need to figure out how to do that, and you'll be proud of yourself when you do. Here is a distribution, and I would like to, here is the center of mass, and I would like to know where that center of mass is for this crescent arc. But if you are clever, instead of treating this as a continuous distribution, which is what it is, I would instead call it a discrete distribution of two things. That I will fill in this void here with mass that is the same as the other mass, and I know in that case, if I fill this in and it's uniform in density, that the center of mass is right there. And so we have that the center of mass is equal to the location of this little thing times the mass that makes up this thing. We're going to have two things here, a discrete distribution. And then we have the crescent, its mass times the location, and its location would be its center of mass. So that's what I'm trying to find, divided by the total mass. And then you plug in the values, and I know that the center of mass here is at 0. This location is negative r. The mass that's there is going to be this uniform density times the area of this disk S. And then this part over here would I'm trying to find where it is, but the mass that is there is going to be the total mass, which would be 4 r squared pi times the density. But I took away that part there, so it's 3 r squared pi times the density. And then we can see that I don't need to know the density. I can divide that out. I can divide out pi. I can divide out r squared. And I'm left with minus r plus that location of the center of mass of the crescent times 3 is equal to 0. So it must be that that location of this center of mass is r over 3 over where this is 2r, that and this is r, that you come 1/3 r over, and that's where the center of mass is. How clever! We shall want to remember that if we ever get into a similar situation. Fact: the sum of the external forces, which we would refer to as the sum, the net force acting on the object, is what causes the center of mass to have acceleration. So if you take the net force, the net external force acting on an object, that is what results in its acceleration. And I hope you would stop for a minute and say, well, what about the internal forces? And then you would reply that the internal forces are all going to be action-reaction pairs, both of which are acting on the object. And so there is no net force there. It will not cause acceleration of the object. It is the external forces who have their reaction pairs acting on other objects that have a net force that adds up to a net acceleration for the object. This is the lab that we're going to do in this unit, that we're going to launch a projectile and then it will explode in the middle of the flight, sending fragments flying off. I have 4 fragments that leave. No, 5. This part here as well. And the question is, well, there could be many questions, but I think the question is going to be, and when you do the lab, is let us find each of these objects at the end and find the center of mass of those 5 objects. And that should be the same as the center of mass of this projectile if it had not exploded. That is to say, are there external forces acting on this? Well, yes. Gravity is an external force acting on this. However, there are no external horizontal forces acting on this. That's projectile motion, right? No external horizontal forces. Therefore, the center of mass will have no horizontal acceleration. It will have vertical acceleration because of the vertical external force, and we would expect the center of mass to rise into the air and to descend. But there will be no acceleration going horizontally, and so the center of mass of the unexploded projectile should be the same, horizontally should be the same as the center of mass of all of the fragments. This is a lovely picture from your book of a woman doing a grand jet, a big jump. Doesn't sound so good when you don't say it in French, does it? But this red dot is her center of mass, that we have cut her up into little bits and weighted each part of her by the mass of each of those little bits, and then added them all up in a continuous distribution, and here's her center of mass. But notice it moves higher in her body. Why? Why would it move higher in her body? Because she raises her arms. Her arms are lower, her arms go up. That's going to raise the center of mass. I think she may also raise her legs slightly. Well, the center of mass, of course, is going to follow a parabolic trajectory. But by raising her arms, which is going to be an internal force, and so is not going to cause any acceleration of the center of mass will follow its well-behaved trajectory due to that external force from gravity and no horizontal forces. But by doing that, she causes her head to stay at the same level. And we, the audience, see that her head stays at the same level, and thus she seems to float for an inordinately long period of time to defy gravity through this trick. Physics! It makes life so beautiful. Lastly, a problem that I think is good, that we have a hollow sphere of radius r and mass m, and inside of it is a sphere that is twice as massive but has a radius of 1/10 r. And I have a little marker to indicate where the center of the spherical shell is. At time 0, I let this go and it rolls down, and of course that's an internal force, so the center of mass cannot accelerate, and so while it is moving this way, the big shell must go that way, and then when it gets over here it rolls back, which causes the big shell to go the other way, and the big shell wobbles back and forth, blah, 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 as this thing moves back and forth, because the center of mass, which started off with no horizontal velocity, must continue to have no horizontal velocity, because there is no external horizontal force. Ultimately, the internal force of friction slows things down and it lands here. And the question is, when it is finally here and stationary, how far has the center of the spherical shell moved relative to that point? And I guess you just admire me while I do the problem. That first I recognize that there's no external force, so there's no change in the horizontal acceleration, which is initially 0 and will continue to be 0, which means that the velocity, which is initially 0, will continue to be 0 horizontally. And then I take this mass, which was located, I'm going to call this my 0 reference point, at, 0.9 r in the negative direction, and this mass, which was located at 0, and then at the end we have the total mass, 3m, located at the center of mass, which is going to be some negative distance over here. Then you just do the arithmetic, and x, this x here, comes out to be negative 0.6 r. How clean, how sweet, if you will just learn how to work with center of mass. Thank you very much.